Communication is another central aspect of multi-agent systems. Agents may share information explicitly through messages or implicitly through actions. In partially observable environments, communication can significantly improve coordination. Learning communication protocols is an active area of research. Agents may learn to encode information into discrete symbols or continuous vectors, developing emergent languages tailored to the task. However, ensuring interpretability, robustness, and alignment with human expectations remains challenging. Scalability is a critical concern. As the number of agents increases, the joint action space grows exponentially. If each of n agents has a possible actions, the joint action space has size a to the power of n. This combinatorial explosion makes naive representations infeasible for large systems. Researchers exploit structures such as locality of interactions, factored representations, mean field approximations, or graph neural networks to model interactions efficiently. In many systems, each agent interacts strongly only with a small subset of neighbors, allowing sparse representations. Mean field approaches approximate the effect of many agents by an aggregate distribution rather than modeling each agent individually. Instead of conditioning on the exact actions of all other agents, an agent conditions on the average behavior of the population. This reduces complexity and can approximate equilibria in large populations. Such approaches are particularly relevant in economics, epidemiology, and swarm robotics, where the number of agents can be very large. Another key issue is partial observability. In many real-world multi-agent systems, each agent has limited information about the global state. It may observe only local signals or noisy measurements. This leads to decentralized partially observable Markov decision processes. Agents must form beliefs about the state and possibly about other agents' beliefs. Recursive belief modeling can quickly become intractable. Practical methods often rely on recurrent neural networks to maintain internal memory states that summarize past observations. Safety and robustness are particularly important in multi-agent environments. When multiple autonomous systems interact, unexpected behaviors can emerge. Small changes in policy may cascade through interactions and produce large system-level effects. In adversarial settings, malicious agents may exploit vulnerabilities in cooperative agents. Robust multi-agent learning aims to ensure stability and performance even in the presence of unpredictable or adversarial behavior. We should also consider evolutionary perspectives. In evolutionary multi-agent systems, strategies evolve over time according to performance. Instead of gradient-based learning, we may use evolutionary algorithms where populations of agents reproduce, mutate, and are selected based on fitness. This can lead to diverse and sometimes surprising behaviors. Coevolution of agents can produce arms races, where improvements in one population drive improvements in another. Such dynamics can foster increasingly sophisticated strategies. Emergent behavior is one of the most fascinating aspects of multi-agent systems. When many simple agents interact under simple rules, complex global patterns can arise. Examples include flocking behavior in birds, traffic waves in highways, or market cycles in economics. In artificial systems, we may observe spontaneous role differentiation, coordinated formations, or the emergence of communication protocols. Understanding and controlling emergence is both scientifically intriguing and practically important. From an architectural standpoint, multi-agent systems can be centralized, decentralized, or hybrid. In centralized systems, a single controller makes decisions for all agents, possibly using a global view. In decentralized systems, each agent has its own controller and limited information. Hybrid systems may use hierarchical structures, where higher-level agents coordinate lower-level ones. The choice of architecture depends on constraints such as communication bandwidth, latency, reliability, and privacy. In practical applications, multi-agent systems appear in autonomous driving, where many vehicles share the road and must coordinate implicitly. They appear in smart grids, where distributed energy producers and consumers interact. They appear in distributed sensor networks, swarm robotics, logistics optimization, financial trading, and online platforms. In each case, the system-level behavior emerges from many interacting decision-makers. Learning stability remains a central research challenge. When multiple agents update their policies simultaneously, feedback loops can destabilize learning. Policy gradient methods, which optimize expected return with respect to policy parameters, must account for the fact that the gradient for one agent depends on the policies of others. In some settings, we analyze learning dynamics using tools from dynamical systems theory. Fixed points correspond to equilibria, and stability analysis determines whether small perturbations will decay or grow. Exploration is more complex in multi-agent settings. An agent's exploratory action may change the environment in ways that affect others' learning. Coordinated exploration may be necessary to discover beneficial joint strategies. However, excessive exploration can destabilize partially learned conventions. Balancing exploration and exploitation becomes intertwined across agents. Another dimension is transfer and generalization. Agents trained in a particular population may overfit to specific partners or opponents. When deployed in new environments with different agents, performance may degrade. Training with diverse populations or using population-based training methods can improve robustness. In cooperative settings, learning conventions that generalize across partners is an active area of study. In summary, multi-agent systems extend the core ideas of artificial intelligence from isolated decision-makers to interactive societies of agents. The presence of multiple agents introduces strategic reasoning, non-stationarity, coordination challenges, communication needs, scalability concerns, and rich emergent phenomena. Theoretical tools from game theory, reinforcement learning, optimization, and dynamical systems intersect in this field. Practically, multi-agent systems are increasingly relevant as autonomous systems proliferate and interact in shared environments. Understanding multi-agent systems requires thinking not only about how a single policy maps observations to actions, but about how policies co-evolve, how equilibria arise, how incentives shape behavior, and how system-level outcomes depend on local rules. By mastering these principles, we gain the ability to design, analyze, and control complex interactive AI systems that operate reliably and effectively in the real world.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.